Hi children, good morning. Good morning to all of you. Welcome to our St. Clair's Phenomenal Class children, right? In the last class we discussed some points children. So what we discussed in the last class means, here we discussed about what is meant by Darwin classification and what is meant by Newland's-Octav's law and what is meant by Mendeleev's classification. Right children? See here, we have to observing here Mendeleev, Darwin and Newland. So those three scientists also, they failed to creating the one of the complete information about periodic table. Right children? So they have some drawbacks. See here Darwin, he was explaining about only some elements. What about Newland? Newland also he was explaining about some few elements. Up to Cauchy level it will be satisfied. After that, for the lowest atomic weights and higher atomic weights, for the elements it does not explain. And Newland does not left any space for the new elements. Okay, children. And here, what are the drawbacks are there in the Newland-Octav's law? It will be clarified by one of the scientists, Mendeleev. Right children? See here, in case of Mendeleev's periodic table also, see here, he left some space. That's what he was lefted. The space is filled by new elements. Like there are 4 elements are there: Eka boron, Eka aluminum, Eka silicon and Eka germanium. So they are named as scandium, titan, scandium, gallium, germanium and technetium. Right children? See here, in case of Mendeleev's periodic table also, we have some limitations. We have some limitations. Here he was corrected the some atomic weights and anomalous space. Or children, anomalous space. In case of anomalous space, here tellurium and iodine. Tellurium and iodine, when you take in this one, tellurium having 127.69, here iodine having 126.9. When we compare these two elements, here tellurium having more atomic weight rather than iodine. But here he was kept a lower atomic weight element, he was kept in last, and a higher atomic weight he was kept in first. So that is the drawback of the Mendeleev's periodic table. Right children? See here, whatever it may be, Mendeleev's what he was proposed in the periodic table. See here, 70% of Mendeleev periodic table is correct. But he was having some limitations. What he was having some limitations means, there is no space for the isotopic forms. And secondly, here in case of Mendeleev's periodic table, there is no mention about what that is noble gas. Right children? So these are some limitations we have in case of Mendeleev's classification. So children, so whatever it may be, when we are taking that here Darwin and Newland's and Mendeleev. So those three scientists also, they was taken as a atomic weight as a property. What children? Atomic weight as a property. So what they were proposed, these three periodic classifications are wrong. Right children? And middle of the some scientists are they proposing, like Luther Mayer also, he was proposing the one of the classification. So those all classifications are wrong. But ultimately here in the year of 1913, one of the scientists, H.J. Moseley, who is the scientist children? H.J. Moseley, he was proposing the one of the periodic table based on the Mendeleev's classification. Right children? Here, based on Mendeleev's classification, he was proposing. But Mendeleev proposed the periodic table based on the atomic weight property. But here, H.J. Moseley, he was taking the one of the new invention, one of the tremendous change in the periodic classification, that is the property based on atomic number. What children? Atomic number. It's very, very important children. Here, based on atomic number. Here, based on atomic number concept, H.J. Moseley, who is the scientist children? H.J. Moseley in the era of 1913, he was proposing the one of the periodic table. Right, children? Here, H.J. Moseley, he was taking the X-rays. He was taking the X-rays. See here, he was taking the X-rays. When he was taking the X-rays, he was bombarded with high resolution of electronic rays. High resolution of electronic rays on metallic plate. High resolution of metallic rays on here X-rays. He was passed on the one of the metallic sheet. Here when he was rejecting the some electrons, it was rejecting the some electrons. Right, children? But here what we have remaining, we have positively charged particles are presented here. Positively charged particles. Here, positively higher resolution of X-rays were kept on one of the metallic sheet. Electrons are rejected from the metallic sheet. Then what will be presented here, children? We have presented here only positive charged particles. So here positive charged particles were considered as a protons. What, children? Positive charged particles considered as a protons. Those protons we are considered as a number of protons. We are considered as a number of protons. We have to consider the atomic number. What, children? Number of protons we have to consider the atomic number. So based on atomic number concept, H.J. Moseley, he was proposed the one of the periodic table. That was the periodic table we have to consider the Moran periodic table. What, children? Moran periodic table, right? So today we are going to discuss about Moran periodic table. What, children? Moran periodic table. It's very important for you, children. See here, each and everyone, you should listen the class very carefully, and we have to take your notebook. You should write all the points in CW, and as well as you have to see the textbook and you have to draw the periodic table also, right, children? And I gave some synopsis through WhatsApp also, right, children? So each and everyone, you should write those synopsis, and as well as you have to listen the lesson, you have to prepare a notes also, right, children? See here, Moran periodic table. Moran periodic table was introduced by which of the scientists, children? H.J. Moseley, right, children? See here, when we are considered that H.J. Moseley, here he was proposing one of the periodic table. That is the periodic table we have to consider as the Moran periodic table. What, children? Moran periodic table. So this is the Moran periodic table. It was proposed in the year of 1913 based on atomic number. Right, children? See here, in case of when we take in our construction of the house. See here, in the construction of the house, what we have? In the construction of the house, main we have the basement. Right, children? What is the main here? Basement. Here basement. After that, after basement, we have to arrange the pillars. So based on pillars, we have to arrange with the help of bricks, cement, and with the help of sand and water, we have to construct the house. And top, we have that is the floor. Right, children? See here, that means in that house we have to divide it as a blocks house. We divide it as a blocks. That means in our language, what we call here kitchen or bedroom or open hall, like that we have to divide it here, right, children? That means one separate block for the particular region, right, children? So same like that here also. Here Moran periodic table was prepared by one of the scientists, H.J. Moseley. He was arranged as a periodic table as a 4 blocks. What are those 4 blocks means? See, children, here those 4 blocks. So how many elements we have, children? Totally 118 elements. Already we know that. How many elements we have? 118 elements. Those 118 elements here, H.J. Moseley, he was arranged in a 4 blocks. How many blocks, children? 4 blocks. What are those 4 blocks means? Here he was arranged those 4 blocks in a 4 blocks. Those we have to consider as S, P, D, F. There are 4 blocks. How many blocks, children? There are four blocks we have: S block, P block, D block, F block. Right, children? So that means here Mendel's periodic table. See here, Mendel's periodic table, 75% of Mendel's periodic table with he was arranging some elements. Right, children? So those 118 elements he was arranged in one of the tabular form. That tabular form we had considered as a long form of the periodic table. What, children? Long form of the periodic table. That is, the long form of periodic table consists of, there are four blocks. Those four blocks are S block, P block, D block and F block. Right, children? Here S block elements can be present in the left side of the periodic table. What, children? S block elements can be present at the left side of the periodic table, and P block elements can be presented at the right side of the periodic table, and D block elements can be presented at in between S and P block elements, and F block elements can be present at the bottom of the periodic table. What, children? Bottom of the periodic table. So this is the bottom of the periodic table. Those elements, F block elements, considered as the basement. So these are the, in our house what we had considered the rooms or particular region we had considered. Same like here, S block, P block, D block and F block. Right, children? Here those S, P, D, F blocks. So totally those 118 elements he was arranged in a 4 blocks. See here, in case of Mendel, he was arranged the periodic table based on the Mendel's periodic law. But here H.C.M. Moseley, he was arranged the elements in the based on the atomic number concept based on the modern periodic law. See, children, what is the modern periodic law, children? So here modern periodic law is the physical and chemical properties of the elements. The physical and chemical properties of the elements are the periodic functions of the atomic number. Or children, periodic functions of the atomic number. Here, after proposing the atomic number also, when we consider the atomic mass means we have to consider the both proton number and electron number. So based on the proton number, we have to consider the atomic number. Based on the valency electrons, we have to consider the electronic configuration. That's why he was added one of the term in the modern periodic law. What is that? Another term is atomic number and electronic configuration. Okay, right, children? Once all of read this. What is the modern periodic law, children? Here, the physical and chemical properties of the elements or the periodic functions of their atomic number or electronic configuration is considered as a modern periodic law. So based on atomic number and electronic configuration, he was arranged the totally 118 elements in a 4 blocks. Right, children? In that 4 blocks, he was arranged in some of the elements in a horizontal rows, some of the elements in a vertical columns. Totally 118 elements. He was arranged in a 4 blocks. In those 4 blocks also, he was arranged in a 18 vertical columns. So those 18 vertical columns we are considered as groups. He was considered as groups and 7 horizontal rows. 7 horizontal rows. 7 horizontal rows we have to consider as the periods. That means here children, modern periodic table consists of how many groups children? Totally 18 groups. How many groups children? 18 groups. And how many periods children? 7 periods. Here modern periodic table consists of 18 groups and 7 periods. 18 groups and 7 periods. Vertical columns are called as groups. Horizontal rows are called as periods. That means here modern period table consists of 18 groups and 7 periods. So what are those 18 groups and 7 periods means? See children, when I draw the periodic table, please everyone should watch this one. Right children? See here, we have those 18 groups means we have to consider as a like hydrogen, lithium, sodium, potassium, rubidium, cesium and francium. Okay children, see here, I will draw here. Totally how many groups we have children? 18 groups and 7 periods. Here hydrogen, lithium, sodium, potassium, rubidium, cesium, francium. Right children? And here beryllium, magnesium, calcium, strontium, barium and radium. Okay. Here thereafter see children, calcium. So here scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Okay children, zinc, cadmium, mercury, copper, silver, iron, nickel, palladium, platinum, cobalt, ruthenium, iridium, iron, ruthenium, osmium, manganese, technetium, rhenium, chromium, molybdenum, tungsten, vanadium, neodymium, thallium, titanium, zirconium, hafnium, scandium, yttrium, lanthanum. Okay, right children? Lanthanum after actinium. What children? Actinium. See here, actinium. After that, we have rutherfordium. What children? Rutherfordium. Then Wm. Then Wm after Seaborgium. Then after Hassium. Then children, borium. Then here what we have, this is the some of the elements we have children. Here rutherfordium, Wm, Seaborgium, Hassium, borium and meitnerium and dermastinium. Okay right children? And here we have some of the elements like here beryllium after what we have children? Beryllium after boron. Here boron, aluminium, gallium, indium and thallium. And here carbon, silicon, germanium, tin, lead. After that nitrogen, phosphorus, arsenic, strontium, this one. Then here oxygen, sulfur, selenium, tellurium, polonium. Then here fluorine, bromine, iodine, acetylene. And finally, helium, neon, argon, krypton, xenon, radon. And here it is organza. Okay, children. Here, these are the elements we have to consider as S-log elements. Or children, S-log elements. So these are the elements we have to consider as P-block elements. Or children, P-block elements. So these are the elements we have to consider as D-block elements. At the bottom of the periodic table, we have F-block elements. What children? F-block elements. See here, totally we have how many F-block elements we have children? Totally 14 elements. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Right children? So F-block elements again 14 and 14, totally 28 elements we have children. See here, please all of look at your textbook. When you are looking at your textbook, you have to easily understand that. Right children? See here, what is the position of S-block elements means left side of the periodic table. What is the position of the P-block elements means right side of the periodic table. What is the position of the D-block elements means middle of the periodic table. And here what is the position of the F-block elements bottom of the periodic table. Again here bottom of the periodic table consists of cerium to lutetium. And here it is here, and we have F-block elements cerium to lutetium, and here here lawrencium, and here cerium. After that it is actinium. Here it is up to lutetium. Right children? Here totally we have 4 blocks children: S-block elements, P-block elements, D-block elements. Here S-block elements, children, how many said? Here 18 groups. How many groups children? Totally 18 groups. 18 groups means here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. How many groups children? Totally 18 groups. And how many periods children? 7 periods. What we have the 7 periods means, here this is the first period, this is the first period, this is the second period, this is the third period, this is the fourth period, fifth period, sixth period, and 7th period. Right children? Here first element based on atomic number 1. Here atomic number 2. 1, 2. Then here it is 3. Here is the atomic number, it is 10. And here 3, 4, 5, 6, 7, 8, 9, 10. And here sodium 11, 12. And here is 13, 14, 15, 16, 17, 18. And here it is 19 element. Potassium is 19, calcium 20, 21, 30, 31, 32, 33, 34, 35, 36. Right children? And here it is 37. And here it is 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54. And here it is 55, 55, 56, 57. So after lanthanum, we have to count the F-block elements children. So what we have the F-block elements children? See here in your textbook, they are given clearly children. See here in your textbook, they are given modern periodic table in your textbook. See here, observe this children. Here what we have here: cerium, praseodymium, neodymium, praseodymium, samarium, erbium, gadolinium. Here promethium, neodymium, promethium, samarium, erbium, gadolinium, erbium, dysprosium, holmium, erbium, thulium, Ytterbium, and sorry, here it is lutetium. What's your name? Lutetium. Then here it is thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, fermium, mendelevium, and nobelium, and lawrencium. These are the elements we have to consider as a block elements. And see children, here rutherfordium, dubnium, seaborgium. After here is borium, and here is borium after hassium, metallium, dermestanium, and romangenium. What children? Romangenium. And copernicium, flavoronium, and here is lavalium. What children? Lavalium. So this is we are considered as a totally periodic table. Right children? Here in this periodic table, S block elements and P block elements. S and P block elements we have to consider as a S into P block, 18 groups and 7 periods. Here S and P block elements we have to consider as a representative elements. Representative elements except noble gases. Except noble gases. And here D block elements we are considered as a transitional elements. What's the name? Transitional elements. And here M block elements. See here M block elements can be present in the D block. How it is? See children, S block we have to consider as a first A and second A group. First A and second A group. And here we have to consider as a third A group, fourth A group, fifth A group, sixth A group, seventh A group, and eighth A group. And here it is first B, second B, third B, fourth B, fifth B, and sixth B. So these three group elements we have to consider as a 8th B. So totally in this periodic table we have to consider as a first A and second A group elements we have to consider as S block elements. And third A, fourth A, fifth A, sixth A, seventh A, eighth A we have to consider as a P block elements. In the P block elements, only S and P block elements except noble gases. So noble gases we will not consider as representative elements. Why? Because of noble gases does not react with any another elements in some exception cases. But here cannot react with any other elements. That's why we have considered as a does not consider as a representative elements. Well, except noble gases, S and P block elements we consider as a representative elements. So D block elements we have to consider as a transitional elements. What's the name? Transitional elements. And here M block elements. After 57 we have to start with 58, that is the cerium. So 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71. And here it is 72. That means here after lanthanum, here cerium to lutetium. So these are the elements can be present in between third B to fourth B. And here it is we have to consider as 86. And here 87th element is francium. And here it is 88. Then here it is 89. And thorium is 90. And lawrencium is 103. And rutherfordium is 104. From 89 to after 90 to 103, these are the elements also can be present in the third B group elements. That means the position of the block elements can be present in third B group. Presented in the third B group. Right children? That's why here block elements we have to consider as it will be present in a transition elements. Inside of the transition elements. That's why we have to consider as a block elements we are called as inner transitional elements. What children? Inner transitional elements. S block elements, S and P block elements except nobody has to consider as a what children? Transition. What that is? Sorry, representative elements. D block elements we have to consider as a transitional elements. F block elements we are called as inner transitional elements. What children? Inner transitional elements. So these are the 4 blocks can be present in the periodic table. Right children? Based on the modern periodic law. Right children? And here, in case of periodic table, here we have to consider that these are the total 118 elements, but he left some space here. That means those are we have considered as unknown elements. Or children, unknown elements. Here, these are we consider as this is we consider as an unprimed. According to the IUPAC nomenclature, we have to consider as an unprimed. That means 113 element. And here is palladium. That means we consider as flavonium. And pentium, septium, hexium, octium. UEO. Octium we consider as oganescium. And here copernicium. And here there is 113 element considered as a according to the IUPAC name. And here unknown quality considered as a flavonium, lavonium, and oganescium. And already they are invented that is considered as a nihonium. What's right? Nihonium and technetium. Nihonium and technetium. And here there is we have to consider as a nihonium, and here there is technetium. What's right? Technetium. So right that. Here they have to already propose that total elements in the periodic table, right children? And here, in case of F block elements, again F block elements will be classified into 2 blocks. How many blocks children? 2 blocks. Here, those 2 blocks can be starting with the lanthanum. So those will be considered as F block elements again classified into 2 blocks. Those blocks considered as lanthanides and octinides. Lanthanides and octinides. And here, lanthanides. Here, block elements will be again classified into 2 blocks, lanthanides and octinides. Lanthanides again we have to consider as radioactive elements. What's the name? Radioactive elements. And here, lanthanum, cerium, promethium, neodymium, promethium, these are considered as rare elements. So finally, lastly, thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, california, iodinium, fermium, gadolinium, nobelium, orange were considered as radioactive elements. That means lanthanides were considered as rare earth metals, and here octanides were considered as radioactive elements. Right children? So this is about some few information about periodic classification of the elements. The remaining concept we discuss tomorrow. Right children? So please all of you please watch these videos and you have to maintain the speed up. Okay children, right? Thank you.